All right, today we're diving into the hidden genius holding our biggest structures together. We're going to look at two totally different, competing ways of building with concrete. You ever look at a massive bridge or maybe a stadium with a wide open roof and just think, how? How in the world do they stretch something like concrete across a huge gap without it just collapsing under its own weight? Well, the secret is in these things, girders. They are the absolute workhorses of the construction world, the backbone that does all the heavy lifting, carrying the load from one side of an open space to the other. So let's get on the same page. A girder is pretty simple. It's a main horizontal beam. Its whole job is to bridge a gap, supporting everything from the cars on a highway to the roof over your head in an arena. But how we make these girders? Well, that's where the engineering magic really starts. Okay, so first, we have to talk about a fundamental problem with one of the most common building materials on the planet. I like to call it the concrete conundrum. On the one hand, concrete is an absolute beast when you put it in compression. You can squeeze it, you can stack incredible amounts of weight on it, and it just doesn't care. It holds up beautifully. But, and this is the whole key to our story today, it is shockingly weak when you try to stretch it. You pull on it, you try to bend it, and it just cracks. This is concrete's Achilles heel. So what does that weakness actually look like? Well, in a standard reinforced concrete girder, we call it RCC, any weight on top makes the beam sag, even just a little. Now, the top part gets compressed, which, concrete loves, but the bottom part gets stretched out. And that stretching, that tension, causes tiny cracks to form. Now, we put steel bars or rebar in there to handle the stretching, but the concrete itself is still cracking. So if you want to cross a longer distance with RCC, you have to make the girder deeper. You have to add more steel. It gets bigger and heavier and heavier. Pretty soon you hit a point where the beam is using most of its strength just to hold itself up. For really long spans, it just becomes completely impractical. And this is where a truly revolutionary idea comes into the picture. A way to get around concrete's natural weakness by, well, basically by giving it a superpower. The thinking was something like this. Okay. Concrete is weak when you stretch it. So what if we just never let it get stretched in the first place? What if we pre-compressed it, squeezed it together so tightly that any future stretching would just be releasing that initial squeeze? Okay, this is the perfect way to picture it. Imagine you have a row of books on a table. If you try to pick them up just from the ends, what happens? They all fall, right? But now squeeze them together really hard from the sides. Suddenly, that compression force holds them all together, and you can lift the entire row like it's one solid block. And that's, right there, is exactly the principle behind prestressed concrete, or PSC. Instead of our hands, engineers use these incredibly strong steel cables called tendons. They use powerful jacks to stretch them, and then they lock them in place, putting the entire concrete girder into a state of permanent compression. So, by definition, prestressed concrete is actively working against the load before it's even there. That built-in squeeze means that when cars and trucks drive over the bridge, the tension they create is basically canceled out by the pre-compression. The concrete never actually feels a net stretching force, and if it never gets stretched, it never cracks. Now, this clever squeeze isn't just a neat party trick. It gives PSC some dramatic, real-world advantages. So let's actually put these two head-to-head and look at the numbers. Right off the bat, a huge difference in size. Because it's so much more efficient, a prestressed girder for a 15-meter span can be almost 30% shallower than a regular RCC girder. That means less material, less weight, and more open space underneath. That's a huge deal. Okay, get ready for this one, because it's just staggering. While PSC uses those special high-strength tendons, it needs way less of the normal steel rebar. For that same 15-meter span, PSC can use up to 90% less reinforcement steel. That is a massive saving in both material and weight. And you know what all those material savings lead to, right? Lower cost. As the spans get longer, prestressing just gets more and more economical. At 15 meters, the prestressed girder can cost over 55% less than its big, bulky RCC counterpart. That's less than half the price. And finally, how does it actually perform? Well, it's not even a fair fight. Because that prestressed girder is actively pushing back against the load, it sags way less. A regular RCC girder can deflect or sag up to 4 times more than a PSC girder. That's the difference between a rock-solid structure and one that feels a little bouncy. So, how do engineers actually do this? How do they apply this incredible squeeze? Well, it's a very precise process, and there are a couple of different ways to do it, with some really tricky things to keep in mind. So, there are two main ways to get the job done. With pre-tensioning, you stretch the steel tendons first in a big casting bed, and then you pour the concrete around them. Once the concrete is hard, you cut the tendons, and that force snaps into the concrete, squeezing it. Then there's post-tensioning, which you see on big on-site projects. Here, you pour the concrete with a hollow tube inside. After it's hardened, you thread the steel tendons through the tube, stretch them with jacks, and then lock them into place. But, it's not as simple as just pulling some cables tight. Engineers basically have to predict the future. They have to calculate and plan for something called pre-stress loss. See, over time, a bunch of things happen. The concrete shrinks a bit as it dries. It also slowly deforms over years under that constant squeezing. That's called creep. And even the high-strength steel itself relaxes just a tiny bit. All these little things reduce that initial squeezing force, and engineers have to account for every single one perfectly in the design. So after hearing all the amazing advantages of pre-stressing, you might be asking yourself, why do we even still use traditional reinforced concrete at all? Well, it really just comes down to picking the right tool for the right job. Here's the final breakdown. For shorter spans, say up to 25 or 30 meters, good old RCC is still king. It's faster to build, it's cheaper for those smaller jobs, and it doesn't need specialized labor. Think parking garages or small buildings. But the moment you need to go big, cross a wide river, build a huge airport terminal, the tables turn completely. That's where PSC shines. It becomes way more economical and is structurally far superior, even though it takes a bit more time and needs special equipment and skills. So the next time you're driving across a long bridge, remember what's happening right under your tires. It isn't just a passive slab of concrete sitting there. It's an active, dynamic structure. It's an engineering marvel that is constantly, powerfully squeezing